Now, the second way you might want to do this is take a look at systems that actually need distributed data. And distributed data is another important aspect of a lot of blockchains. Here in Wyoming, we're tracking cows on a blockchain. And one of the nice things about Ethereum, it's being done on a private Ethereum network, is that Ethereum works well with really bad networks for distributing data. As in, if a node goes offline and comes back on 2 days later because it's on a ranch that's way out in the middle of nowhere, they can still synchronize and it'll pick up where it left off and it won't lose data. So that distributed data is a useful thing. This system that I'm going to describe here, this is a second one that's similar to, but different than the other one, is also being used in a mine in Peru to prevent a bunch of forgery. They used to pay their miners 8 to 10 days after they actually delivered stuff to a central office. By using a system like this, they're now paying them the same day that they deliver stuff because they can prove that it isn't a forgery. And I did mention that we're using this kind of a system for some stuff in food tracking here in the state of Wyoming. Now, the things that Postgres doesn't have in it that you kind of need if you're actually going to do this is strong signatures and verification of strong signatures. It doesn't have P2P communication. At least to the best of my knowledge, it doesn't. I'm using a system for person-to-person communication in Go. And there's no good way of building a full-fledged HTTPS server inside Postgres itself. So what I've done is I've built those things outside. And this is somewhere between a version 2 and a version 3 system. I'm using the same concept as Definity's 9 nodes. So although I'm running 30 nodes in the network currently, it randomly picks basically 16, which guarantees to me that half plus 1 of 16 is 9. And the way that it works is there is a random number source that picks the nodes that are actually going to do the work. So if you scale to more nodes, it would not increase the amount of nodes that are running stuff in any cycle. So the start of a block is it gets a random number. Transactions are shared. Any node in the network, when it receives a transaction, forwards it to all the other nodes. And the nodes, that 16 that are actually running things, say, okay, I'm going to take this transaction at this point, include it in my set of pending transactions. After 5 seconds of picking up transactions, it turns around and it does its first consensus thing, which is the 16 nodes each send to each other the set of transactions that they're going to run. Now, it turns out that by doing this, we can get consensus because 9 of them will have, or more, will have a set that they are going to run that is common. And this doesn't happen every time, but in the past year of running this, about once a month, they won't agree on a single transaction. If they fail to reach consensus because of network glitches or something like that, then all of the transactions are simply pushed to the next 10-second round. They run the transactions. If a nodes get any transactions in between, then they take those transactions, they just push it forward to the next run around this loop. And at the end of running the transactions, they share all of this again with a Merkle hash. They share the blocks and the transactions to the entire network. And this runs about every 10 seconds. I wouldn't say exactly 10, but 10 seconds with maybe a half a second drift is the time. To compare that, Ethereum is doing a similar kind of thing in 22 and 7/10 seconds across 11,000 nodes. So the kind of model is I took the same table as the other one. I added a Merkle hash field, and I added a second table that has the transactions in it. And what is a transaction in this case? It is transfer of some amount of funds from some previous transactions to some new transactions and an amount. And at the end of that, it has a hash and a signature. The signature is the authorization from the from account to do this transfer. So it validates the signature, and when the signature is valid, it will run a set of these transactions. And realistically, the piece that is most useful, as far as I'm concerned, is that very last field in the transactions, which is a memo. You look at a lot of stuff like the mine in Peru, and what are they really using out of this? They're sending zero value transactions with a memo that has the data that they want to store and synchronize across all of their nodes. So they transfer no money or no tokens, but they have this memo, and that's where they're hiding their data or sending their data, but it gets synchronized across their different nodes, and consequently, it's very useful to them. And what did I do in the trigger that does the blocks? On line 11, I added that Merkle hash. It's in red there. So it really isn't much changed. And how do I get transactions into this system? You could do this with a browser, but it's a nuisance to type these things in, and you have to generate a signature. Realistically, the people that are using systems like this have keys, and they take the key and do a digital signature in software. But what does it have in terms of sending a transaction on a node? It has a from address, a to address, which are the accounts that have the transactions, a signature for this, which is the signature that could be used to verify that the from person has the correct signing key, and an amount. 0 is what I think is used most, and a memo. Now, inside the system, this is a full-fledged, you could say it's a cryptocurrency, but it I don't think is being used much that way. It is more useful for getting the benefits of shared data across nodes with proof of immutability. The random assignment stuff allows this to run with a cycle time of about 10 per second. And, the transactions, I don't think, make much difference to people. What they're using it for is really the shared reliable data. This is built on top of it's a Go program. It's about 1,500 lines of code alongside a Postgres database that handles the web services and the P2P. So it's not a huge amount of code. It has the same back-end piece that's a separate piece that writes it to a node in Ethereum for proof of immutability of the hashes and the signatures. So the cycle really starts with this random number. It picks one up, 5 seconds of accepting transactions, a run that rarely is over the time because I have never seen it run over the 5 seconds, when it just posts those saved transactions to the next cycle. And it doesn't matter which node gets the input, it propagates it across the system. And at the end of this, the 9 nodes that actually agreed, or more up to 16, all share the blocks that have the end result in it. So everyone sees the result for a very fixed amount of effort. So you could have more than 30 in here. The reason for 30 nodes is that's enough to guarantee that it is very difficult for any one node to be able to cheat, or if there's one that fails, it doesn't make any difference. If you take one out, there's still plenty of nodes there to guarantee the system runs. And what is a Merkle hash? Because that Merkle hash is the guarantee that the transactions themselves are in order and basically immutable. And it turns out that each transaction has a hash in it. Then we take hashes of those transactions in pairs, and we combine them until we get down to a single hash, and that's what gets stored in the block. And there's been really good research to prove that this basically guarantees the position of each of these, guarantees each one of these are unchanged, and you can't fake Merkle hashes. The hashing scheme used here is SHA-256 all the way through. So it gives you strong proof that the blocks in the transactions, the rows in the transactions, are actually the ones you expect to have. Now, how do I guarantee the order? When I go to do a Merkle hash, it's using UUIDs, and it actually sorts on the UUIDs in a particular set of transactions. So they're sorted, not necessarily in any particular order since they're UUIDs, but it gets a consistent order, and that order is guaranteed across the entire network. So what does it cost for me to run one of these systems? I run 10 in-house nodes and 20 on a combination of DigitalOcean, 10 of them, and 10 of them at Amazon Web Services for around $100 a month. And I don't have any cost other than the electricity for the 10 in-house systems, which is not a huge amount. Now, the trade-off here for getting this distributed consensus is that you have latency of about 10 seconds, which you think about us inserting a row in Postgres and there isn't much latency. It's a really good system. But here we have realistically 10 seconds and everybody sees the transactions. And I've only run it to about 40 transactions a second, which is about 400 at a time. It probably would do more, but I have not tried it. And it's not a huge, complicated piece of code. It's 1,500 lines of code-ish, maybe 1,400. It's based on using this Go library called libp2p that is heavily used for things, a bunch of different things. It's the same library that's used inside Ethereum for their communication and is very, very good at this. It does have a lot of asynchronous code. So the code is reasonably complex. So kind of conclusion, the thing that I would say is the important stuff to take away from this is that before jumping into something using any kind of a blockchain, it's important to really look at what the features are that you need out of that blockchain and pick a chain that is appropriate for exactly what you need, because there can be a lot of cost, latency that outside of blockchains you're not thinking about. And there are other alternatives out there today, like, CockroachDB does an amazing job of if you just need distributed data. And the first part of this presentation, if you need immutable data, it's fairly easy to build a system that you can guarantee you have immutable data. So before building out something that is actually in a blockchain, the cost and the latency are factors that you've got to deal with, and you've got to say, is this worth doing in Ethereum? And there are cases that there are. I'm not saying that there aren't. I wrote the contracts for a company in Atlanta that is doing property titles on a blockchain. And, a property title search, they're going to charge, I think, $40. And it will be basically guaranteed, as opposed to the average in the US of $3,000 some dollars that it takes currently to do a title search and title insurance, because it's not guaranteed to be accurate. So there are cases where it makes sense, but there are an awful lot of other things that you can get some benefit from having a blockchain with other alternatives and build it with either a centralized database or a series of them and get a lot of benefit. The other things that I'm still working on is right now my random number source. I'm using NIST for a random number source, which is a global oracle for random numbers. There is a way to use the Byzantine fault tolerance honey badger stuff to generate distributed random numbers. I'm working on building that into this. And also building in so that we can do stored procedures as basically contracts, smart contracts in the system. And there is a link here to the source code for these two different approaches to building blockchains. So with that, Lindsay, do people have questions or?
So we've gotten one question so far. Everyone go ahead and get your questions in now if you have them. The first one, and I made a note here, is this question came up with the processing cycle slide.
Yes.
Why 16 nodes? Wouldn't an odd number be better?
The mathematical proof from Dfinity on the 9 nodes says that you get the same level of security out of any randomly chosen set of 9 out of a network. And they actually did some fairly complex mathematical proof on that. And if I pick 16 nodes, I get half of that number, 8, plus 1 additional, so that I've achieved consensus, as in that is a majority of agreed, makes 9. So 16 nodes is just enough to guarantee me the security when also at the same time dealing with the consensus problem, as in I've guaranteed that if those 16 nodes, if 9 of them agree, as in this is the set of transactions we're going to run, or this is the final result of running those transactions, I have a n plus 1/2 plus 1 vote that guarantees that those are consistent. So yeah, it's kind of an odd thing to look at 16 as the right number, but it comes down to half of 16 is 8 plus 1 is sufficient proof. And also gets the Lamport talked about in his 82 paper, how you do voting of half of your nodes plus 1. So this is half plus 1 is 9.
Wonderful. Another question has come in. Why did you choose Ethereum instead of Bitcoin to store your hash?
Ethereum runs in a cycle time of 22 and a half, 22 and 7/10 seconds, with basically a guarantee that transaction is finalized 4 cycles later, that it will not be changed, which is under a minute. Whereas Bitcoin runs in a cycle time of 10 minutes with a guarantee that your transaction is finalized after 6 additional transactions are written. So a Bitcoin transaction is not actually finalized for an hour. So that's the primary reason. And there's no deep technical reason. It's just a question of timing and latency. And I think that with Ethereum version 2 running as basically a proof of authority private network, that the cycle time on Ethereum will be better than the 22 seconds you see now. You can actually drop that to much shorter cycle times. But I have yet to actually set that up and prove that. It will take a while. They just released it a month or so ago.
Wonderful. Those are the questions that we got in. So I think if there's nothing else, I just want to say thank you. Thank you, Philip. This was fabulous. I learned so much. And also thank you to all of our attendees for spending a little bit of your day with us. So regardless of where you are, whether it's morning, noon, or evening, I hope you have a great rest of your day, and I'll see you back here on future Postgres conference webinars.